All right, so what is the meaning of sampling of continuous signals? I'm going to talk about this in a bit of detail, but roughly speaking, what we are talking about here is trying to understand when we can recover a continuous time signal if we are given only the value taken by this signal at some time instance. Like if I take a continuous time signal and I sample it, which means I get access only to the values taken by this signal at say time t equal to 0, some capital T seconds, 2 times t seconds, so on and so forth, but I've lost all the other information. Now the question is, when can I recover my x of t back from just these samples? This is kind of what I want to talk about, but before we go into a bit more of a detail and set the problem up precisely, I want to start by recalling a few simple results about the continuous time Fourier transform that we will need. So I will start with the preliminaries. This is stuff that we have already seen in class before, but nevertheless it may be a good idea to quickly recall them because I will be using them later on in the class. So the first thing I want to talk about is the Fourier transform of an impulse train. So what I mean by that is, suppose I had a continuous time signal p of t given by summation n going from negative infinity to positive infinity, delta of t minus n times capital T. So capital T is just some parameter here, it's some constant, and we have this signal which we call the impulse train. If I were to plot the signal looks like this. It's a train of impulses occurring at time instance 0, capital T, 2 times t, so on and so forth, integer multiples of t. So this is not a new signal. Does everybody remember having seen this? Right. So first thing I want to talk about is what would be the Fourier transform of this signal. How could we compute the Fourier transform of this signal? Well, let's call that as p of j omega. Any thoughts on how we can compute the Fourier transform of this signal? Okay, that would work. Read it off the table. That would definitely work. Just to recall how we got the table entry in the first place. This is a periodic signal, right? So what do we know about the Fourier transform of periodic signals? Well, we could find the Fourier series representation of the periodic signal, and then the Fourier transform can be obtained from the Fourier series coefficients. So if we look at any one period of the signal, let me call that p tilde of t, it's just an impulse with a strength of 1. Right? That's just one period of the signal. And what would be the Fourier series coefficients of this signal? P of k. Well, the Fourier series coefficients can be obtained from the expression which says that you can compute 1 over t times the integral 0 to t p tilde of t, but you can see that p tilde of t is actually nothing but delta of t. Delta of t times e raised to negative j k omega naught t. And what's omega naught? 2 pi over t. And what does this integral evaluate to? Integral delta of t times something dt. Yeah, so this is simply this function evaluated at t equal to 0, right, which is 1. So what this means is that all the Fourier series coefficients are simply 1 over t. So this means for all. I could even just write for all. We're not going to see this too many times. Okay. So now that we have the Fourier series coefficients, what is the Fourier transform of P of t? Well, our result tells us that you take 2 pi times the Fourier series coefficient times delta of omega minus k times omega naught, or 2 pi over t. Sum this for k going from negative infinity to positive infinity, and that's the Fourier transform of P of t. So if we plug in the expression for P of k, which is 1 over t, then we simply get 2 pi over t times summation delta of omega minus k times 2 pi over t, k going from negative infinity to positive infinity. Okay. So if I were to sketch this, how would this look if we were to sketch this? What kind of a signal is P of j omega? What did we say P of t was? It's an impulse train. So what is P of j omega? It's also an impulse train, right? It's also an impulse train. It's just that the spacing between the impulses, or the period at which the impulses are occurring, is different from that of P of t. In fact, it's inversely related to t. So if you think about this signal, what this says is this is a bunch of impulses, each one occurring at integer multiples of 2 pi over t. And then the strength of the impulses are all 2 pi over t. So if I were to plot the Fourier transform, this would be a train of impulses. It's important to pay attention to the spacing of the impulses. So the spacing of the impulses is 2 pi over t apart. So this is 2 times 2 pi over t, so on and so forth. And the strength is 2 pi over t. Does that make sense? This result will be important in the class, so if you have questions, please ask me now. Okay, good. I also want to recall the multiplication convolution relationship, which basically says if I had a signal x of t whose Fourier transform is x of j omega, another signal p of t whose Fourier transform is p of j omega, then the product of x of t and p of t is another time domain signal whose Fourier transform is given by 1 over 2 pi times the convolution of x of j omega and p of j omega. Right? Okay, and the last thing I want to recall before I move forward is convolution with an impulse function. Suppose I had the Fourier transform x of j omega, some arbitrary Fourier transform. What is x of j omega convolved with, let us say, delta of omega minus some omega naught? This is x of j omega minus omega naught, right? So pictorially, what is going on is, if I had some Fourier transform, let me call this x of j omega, when I convolve this with a delta function, delta of omega minus omega naught, the result is simply going to be, let us say this is 0. So the result is simply going to be x of j omega shifted by omega naught to the right. So convolving with a shifted delta function or an impulse function really shifts the signal. Okay? So the result would look like something like this. Okay? So these things, just some preliminaries that I want to recall.